So number 43 like I said, it's a really good example for when I want to use linear combination because notice neither one of them has a GCF and neither one of them has same coefficients. Yeah. So what I want to do here is I'm going to multiply this top equation by 2. And when I do that, I'm just going to rewrite it directly below the second equation. I get negative 4x plus 6y is 40. And now you split into the 3 problems, and you, just like you were just saying, you're going to add them together because it eliminates one of the variables. What linear combination does is that you're just using some scalar to create elimination. That's what it's called. Linear combination, that's what it's called. All right, so add these together, we get what? 0, 10y, and what is that, 25? So y is 2.5. Throw it back in and go. Not too bad? You guys finish it, or are you okay? Yes, absolutely, absolutely. I just saw that because I have a 10, I just thought of 2.5. Ladies and gentlemen, because I knew that what I would do then is just go back to here, because if I double it, it's 10. It's just, in my mind, that was just a quicker way of doing it. What else you got? Now, I know I've had people ask a little bit about the first couple of the word problems there. I don't want to go through all of them yet, because believe it or not, they actually get easier as we go further into this. That first one we were talking about, buying all the boxes of greeting cards, them and reselling them. What it said in that problem was that you had a $36 upfront cost on supplies. And you were also going to purchase a certain amount of boxes of blank greeting cards. You knew that each box of greeting cards cost you $3.50. You knew that also you were going to sell them for $5 a piece. So what was happening here in that one was you have your initial startup cost of $36 for like your paints and your pens and whatever the supplies were. And then you also were going to purchase a certain amount of, I'll use B for boxes. And you wanted to know where the break-even point was at selling them for $5 a piece. Okay. This one, it wanted you to, it's more of a single variable problem than it is the double. As we get into the 2 variable problems, those actually become a little bit easier to work with than these two. Here you just have variables on both sides, subtract the 3.5, set it in, divide out by the 1.5, and that gives you your answer. Okay. That's how many boxes you'd have to sell to break even. Anything over that is profit. Think of it this way. Have you guys ever had a lemonade stand? All right. If you had a lemonade stand, your parents would, you'd have a little lemonade stand. It's a really large lemonade stand. So, it's a really large lemonade stand, and let's say your parents went out and bought you packed lemonade, some cups, and all that other stuff, and they spent $15 on supplies for you, and then you were only going to sell it for $5 or 50 cents per. It's kind of along the same idea as if you're selling it for 50 cents a cup, how many cups would you have to sell to break even to the $15? And then anything over that would have been profit. It's the same basic idea with this one, but you had a separate purchase alongside of it. That's what it looked like. It was funny. We took the kids over to the Sycamore had fireworks on, like, was it Saturday night? Yeah, Saturday night was spring firework night. We were driving through the neighborhoods and we saw a lemonade stand, and obviously it was later in the afternoon. It was 7:30 or 7 o'clock or 7:30. So they hung on the sign on the door on the lemonade stand. It said "Gone Fishing." You know how people do it when they're close their shops and say "Gone Fishing." I thought it was really No, don't lie. You just don't care. I get it. No, that wasn't what I was getting at about American business going out of business, going bankrupt. I was saying that they were closed for the day because they went fishing. There's a difference between going out of business and going fishing.
Fishing is killing our economy.
Is it really? I think you guys are just, at this point, I think you guys are just grasping. You're just grasping at straws here, and you're trying to get me to go hook, line, and sinker for your. So here's my plan. Tomorrow we have that half day, and we have that half day on tomorrow. So what I plan on doing is, instead of trying to get quizzes back to you guys today, I'm gonna do that tomorrow. Okay? Tomorrow it'd be only about 20 minutes, 25 minutes long. That's perfect because I want to actually spend a little bit of time on a couple of the questions you guys screwed up on the quiz tomorrow. And then what we're going to do then on Friday is, as instead of starting the actual word problems over weekends, which I know you wouldn't do over the weekend anyway, what we'll do is we'll do the basic constraint stuff on Friday, which is just all quick graphs. Then on Monday we'll start word problems because that way we'll just get back in the roll of things. So does that seem like a decent? It's kind of a little bit of a shift here, just pushing a day off here. Okay. All right, so let's get started then in 3.3. 3.3 is very similar to what you just did, but what we're going to do is we're just going to graph. Yes, sir.
Oh.
What's that? What? What? I wasn't listening. So here's what I want to do today. Today what I want to get going in is we're going to start with systems of inequalities, and we're going to kind of do rapid overlaps. And I want to take a couple and pass them around. And great. You guys are lucky to get to figure out. I will make some more copies of the good graph paper. Now, hey guys, what changes between this and when we did just that? That's it. That's it. So the only thing that changes, guys, between this problem and this problem is that there are two of them. There's two of them on one piece of graph paper. Now, I could put three of them on there. I could put four of them on there. I could constrain it to a singular. I could constrain it to being within a specific quadrant if I wanted to. Okay? So this stuff doesn't change. Okay? Now, these two inequalities are written out to you in terms of, remember, standard form? They're given to you in standard form. So can you plot via quick graphs if you'd like?
Yes.
Could you plot via the slope-intercept form if you'd like?
Yes.
Yeah. Does it matter?
No.
One way is a little bit easier than the other. So I like to use quick graphs. I want you guys to get accustomed to using quick graphs because as we get into 3.4 is where this all kind of culminates into craziness. The quick graphs are going to be your best friend because you're going to be able to figure out shaded region areas, and you're also going to be able to look at specific domains of where the problems themselves are going to occur. So if we do quick graphs, you guys remember what I mean by quick graphs?
Yeah.
Cover it all? Okay. So if I cover up the 3x and solve for y, where's my y-intercept? -2, good. So if I put my y-intercept at -2, my x-intercept will be at 2/3. Okay, can we fudge where 2/3 is on a graph? Close-ish? Fine. All right. Now, when I go and connect those two dots, are those two dots going to be, when I connect them, going to be solid between them or dotted? Why? Because it's equal. Good, good, good. See how this is a little bit of review and refresh from last little chunk of stuff? Okay. Now, did that graph go through the origin? No. So I'm going to use 0, 0 as my test point. Remember, inequalities create what are called half planes. Half of the graph is true, half of the graph is false. What I want to do is decide whether or not what side is going to be true in order to shade it. So what is 3 times 0? What's 0 minus 0? Is 0 smaller than 2? All right. So that means it's true up here. Now this is where I want you guys just to graph like that. I know a lot of you want to go, don't do that. It's going to be a lot easier. It's going to be a, yes ma'am. You always want to cover the truth. Remember when you did this problem? When it was, hey guys, just a reminder of what side you graph on. When you had a single variable problem, you graphed the number line. You put 7 in the middle, 0 was down here, 10 was over here. You'd circle it and ask, do you fill in the dot? In this case, I would not. And which way are numbers smaller than 7? Left. So basically, I'm testing it at 0. Is 0 smaller than 7? So it's true this side. What changes? Sorry. Now, going back to the other one, it's the same basic idea. Instead of being one variable, you have 2. So you're testing it at the ordered pair of 0, 0. Because here, is it true or false? Is if I substitute in the value of 0, 0 for x and y, is it true or is it false? That's what we're doing. Does that make more sense? Okay. Now, go back to the next one. What is your x and y intercepts of the second problem? Well, the second one has us at 2 and 1. So I have an x-intercept of 1, y-intercept of 2. Is it solid or dotted between the two? Solid. Did that one go through the origin? No. So let's see. 2 times 0 plus 0 is 0. Is that smaller or equal to 2? Yes. So it is also shaded this way. So what occurs here is that you get an overlap shaded region that satisfies both inequalities. Okay? As opposed to solving for the specific point at which those two intersect, we're looking for all possible values within the domain that generate range that'll be all shared. All right? So that means that anything that is within this boundary, all of these values from here to here would work. That's what that means. I can pick any x and y coordinate, any coordinate within that boundary, and it'll be a solution to either one of those inequalities. That's what we're looking at today. 2 graphs, 1 graph paper. We're saving paper. Environmentalists among us all. Okay. All right. Sam, I am. What's that? Yeah, you sign up for it. Come on into the meeting. We'll give you a pre-test and put you in the right type of thing that will be good for you. Our first meeting will be next week. Yeah. Seven and I are going to figure that out. We're going to do a couple different ones. We'll do one probably on Monday after school, and then we'll probably do one either Tuesday after school and then Wednesday mornings. We move to figure out how it's going to work. And I know people have like thousands and thousands of things after school and before school. We try to figure out the best way that it works. And if you guys swing during flex or something like that, hey, we're good. All right, this one is given to you in slope-intercept form, which means it changes the way that you graph it. So when you graph things that are in slope-intercept form, where do you start your graph? Y-intercept, very good. So on the first one, what's your y-intercept? -1. What's your slope? 3, -3. So if your slope is -3, what's the first step to do? Down 3/1. What direction are you going over, left or right? Correct. So same basic principle here, ladies and gentlemen. Whereas instead of being in cover and solve format, we're in point or slope-intercept form. So you start at -1. Down 3, 1. Bless you. Up 3, 1, 1. And so on. Between those two, do I connect them with a solid or a dotted line? Solid, very good, very good. Does this one go through the origin? No, we know it won't go through the origin because the y-intercept is at -1. Okay? The only way that would have gone through the origin if it was the actual equation x equals 0 or y equals 0 for each problem. So we check it. Is 0 greater than or equal to -3 times 0 minus 1? Is 0 bigger than -1? Yes. So that means I'm going to shade to the right of it. Okay. We go to the next one. Y is less than x plus 2. So if y is less than x plus 2, what is your y-intercept? Slope of? Very good. Is it a solid or a dotted line to go through that? Dotted line. Did it go through the origin? Nope. Is 0 smaller than 0 plus 2? Yes. So I'm shading towards 0. And a lot of times, do you see why I am just using like those little dashed lines to shade? Because I'm just looking at finding region, and it's easier to see as opposed to going. Even though the satisfaction of filling in blanks, it makes you feel good, because I know that's why you're doing it. So oh, you just make the sound as you're doing. Yeah, it doesn't work as well. It's like you're spray painting. Now, I want you to try this. I want you to try this without a graph paper. Okay? Now, this is the idea of understanding where certain values are occurring. Okay? Now, x is greater than or equal to 0, y is greater than or equal to 0. What I want you to do is just visualize in your head, where does that occur on a graph paper? Which quadrant is that? Top right quadrant was quadrant number 1. We'll get there eventually. There's only 4 of them. You have 25% chance. remember, just a little heads up in case you had forgotten, x is positive, y is positive, x is negative, y is positive, x is negative, y is negative, x is positive, y is negative. Oh, just so you remember this, cosine, sine, cosine, sine, cosine, sine, cosine, sine. Put down on your little calendar phone for like an alert for like middle of February, and just say Murphy said on September 13th cosine sine is xy. Just middle of February. Pick February 8th. Pick an alarm to go off at like 8:15. Just to remind yourself that Murphy said this back in September. That's Connor's birthday. It's your birthday? You're a Valentine's Day baby too? So is my kid. Who's? Oh, really? Which means that just so you guys are aware that there's reasons why we show you guys certain things first semester to kind of remind you that at some point in time you're going to hear it again. So just remember, cosine is positive, sine is positive, cosine is negative, sine is positive, and so on and so on. It all deals with it is awesome. I love the unit circle. Anyway, back to this. Now, what I want you guys to think of here is when x is greater than or equal to 0, that means you're going to the right. When y is greater than or equal to 0, it means you're moving up. So that means this is what we call a first quadrant problem. That means all I have to do is draw the first quadrant. Because what direction is x positive? Going to the right. What direction is y positive? Going up. Does that make sense?
Yes.
It's one of those things that you can be given specific parameters to tell you what quadrant something's going to occur in. Now, 4x plus 3y is less than or equal to 24. That's a prime example of using what to graph? Quick graphs, cover and solve. Okay? Cover and solve. What's your y-intercept? What's your x-intercept? Okay? About here. And about here. Connect the dots. Solid or dotted? Okay? I know I've with the other parameters, it's only going to go within that section because everything else beyond that, x will be negative or y would be negative. And we don't want that. So what's 4 times 0? Well, let me ask this. Did this go through the origin? Is the origin still here at 0, 0? Okay. What's 4 times 0? What's 3 times 0? What's 0 plus 0? Is 0 smaller than or equal to 24? So which direction is that being shaded in? Being shaded inward, isn't it? So you wind up with this shaded region right there. I'm just showing you right now of what you created. What shape did you create? A triangle with endpoints, with specific length endpoints, didn't you? What's the length of the hypotenuse? Very good. 10. Is here 6, 8, 10. Oh man, I am just making your brains hurt this morning. This is great. Yeah, well, just the sheer going, oh crap, in your minds between showing you ordered pairs and geometry. All right. All right. do a shaded region off of this. Yeah, use graph paper on this one. See how you can do it with the graph paper. Now remember, when you are drawing your lines then, for what values can you stop? Where does this graph stop you? Now, Matthew, what kind of a line is x equal a number? It's a vertical one, isn't it? All right. I know it's a vertical line, but remember which way is x greater than 0? It's going this way. Even though it's vertical, it puts everything going to the right. So you're only looking at quadrants 1 and 4. Remember, quadrants go counterclockwise.
Why couldn't I name that?
All students take calculus. What's positive? Everything's positive. Sine is positive. Tangent is positive. Cosine is positive. Oh, this is going to be awesome. Have I mentioned to you guys yet how much I love teaching trig? This is all little precursors, just so you guys, like I said, your phone's alarm's going to go off in the middle of February and go, Murphy said, September 13th. If you want, it doesn't matter to me. Okay? So when we start this one out, now what I would do is I know that the first inequality there tells me that it's x is greater than or equal to 0, which means it has to be the vertical line at 0 and it's moving towards the right. So all I'm going to do is just draw two arrows, one in the quadrant 1 and one in quadrant 4. By doing that, that means the rest of the problem I'm just going to be looking in those two regions. Okay. The next one I have y is greater than 2x minus 1, which means I have to start my graph where? At -1. Now, this being a greater than symbol, we know that I'm going to be here, and then I go up 2 over 1, up 2 over 1, up 2 over 1, so on and so on. Is that going to be solid or dotted? Dotted line. Okay. Okay. What is 0 bigger than 0 minus 1? Is 0 greater than that? Okay, so it's true moving upward. That other line is that vertical at x is greater. Then I do that again at 3. Up 2 over 1, up 2 over 1 at y-intercept of 3. Now, excuse me, is 0 greater than 0 plus 3? Bless you. No, so it is false at 0, which means going to be true above again. So now this, the truly only shaded region that the overlap occurs, it would be this little wedge in this area.
No, it's not a triangle.
Because this is, remember the black still comes up towards it, so it's just going to be wherever this goes, going all the way up through it here. Okay. There is no maximum to that. There's a minimum. There's no maximum. Okay? We'll worry about maximum and minimums Friday. Okay? When we start talking, we actually throw a constraint to the problem, which occurs. Okay? Now, a lot of times also what you can create, oops, this one's a little bit tougher to write equations off of. Yeah. And I'm going to switch all of these to yeah. Now, I would like you to try and graph this without the use of a graph paper. And really, the only reason why I'm asking you to do that for this one again is kind of a preemptive for Friday. Yeah, Friday, we're not going to use graph paper come Friday. So I just want to try another one with the idea of what direction things are going. So we have y is greater than or equal to 0, x is less than or equal to 5, x is greater than or equal to -3, and y is less than or equal to 4. Which means you have to remember a few things. When y equals a number, what kind of a line is it? Horizontal. When x equals a number, what kind of a line is it? Vertical. Okay. So we start with y is greater than or equal to 0. Okay. So I label it. Y greater than or equal to 0. Which direction is that going to happen? Up, right? Now I have two x values to throw in. X is less than or equal to 5, and x is greater than or equal to -3. So -3 on one side, 5 on the other, and they become vertical. You don't need to worry about that. Now, guys, remember, all I've done here, all I'm doing is I'm taking each individual inequality and giving it a direction. And now I have, what, less than or equal to 4. So I got to put a lid on it. Yeah, pretty much. So if you think about what's created, you create a rectangle. You create a rectangle with specific ordered pairs. Where the intersection of each of the verticals and the horizontals occur are the vertices of that. We know that the vertex at this would be at -3. -3 and 0. -3, 4. Here's 5 and 4. And here's 5 and 0. What you've done is you've created a rectangle given horizontal and vertical lines. Now, if you draw that on graph paper, it's really, really easy. What I'm trying to get you guys in the habit of doing is actually just picking a spot within space and just saying that's what it is. Get past the idea of I have to have a scale. It doesn't matter your scale. It's a visual representation of horizontal and vertical lines that intersect at specific values. That's what I'm trying to get you at here. It takes a little while to get used to this, and it's fine. I just want to start to show you as we get into this, we'll throw in parameters, and eventually we'll have lines that go through that we'll have to find the intersection of, which you're using systems of equations to solve for. And then you'll have constraints built in. You're already from me. I'm sorry. Baby steps. We're just taking baby steps. I did. Well, I did literally throw it at you. Yeah, I probably will. All right, let me give you a few of these to do for the evening. Oh, I just realized I didn't put the PDF file on that calendar. I will do that for an hour. So, let's do this. You guys all have a second graph paper, right? All right. All right. If you give me a quick sec, I'll pull this up. You guys can take a picture of it. Otherwise, I'll have the PDF file downloaded to the calendar. I just realized I forgot to do that. I apparently don't like you guys, so there's that. Yeah, I know. All right, here's those 9. If you guys want to take a picture of it real quick. Otherwise, like I said, I'll have it uploaded on the calendar here in a couple minutes.